Hello, my name is Ruizhe Li from Keio University. The title of our study is Automatic Generation of 3D Natural Anime-like Non-Player Characters with Machine Learning. My presentation today is divided into 5 parts, which begins with background, then followed by an overview of the proposed system, the result of the design neural network, quantitative and subjective evaluation of the generate characters, and ends with conclusion on future work. First, I would like to introduce some background about our study. Non-player characters, NPCs for short, are the characters that are not controlled by a player in a game. In general, we divided them into two types, main NPC and sub-NPC. Main NPCs may play important roles in the main story, or they may do business and provide missions to the player. Usually, they have fixed appearances and fixed names that were set by the game creators, and even some of them have fixed places in the scene. The other type of NPCs, sub-NPCs, walk back and forth in the scene, which can be considered as a part of the background. When they are out of the player's view, they would be deleted to release the computer memory, and new NPCs would be generated around the player at the same time. Our study mainly focuses on sub-NPCs because they don't have fixed appearances and a rich variety of NPCs should be generated to create a good atmosphere in a cyber city. So let's take some examples from the real games. Reza and Ys 9 are both role-playing games released in 2019. At the different places, we can find two or more characters with the same appearances, which makes the player feel strange and may find it difficult to concentrate on the gameplay. The game creators just rely on several specific character models and randomly put them into the scene, but they might not prepare a sufficient number of prefabricated NPC models due to a lack of time, which leads to this kind of problem: high similarity among the NPCs. So our purpose is to automatically generate a rich variety of 3D NPCs in real time. Game creators would be able to create a cyber city with various NPCs more quickly with some simple options, such as the character style and the seasons of the scene. In the present study, we focus only on the appearances of the female student NPCs, as shown here. To create 3D characters, besides traditional 3D modeling by artists, several studies generate 3D models from 2D images like portrait photographs. However, those studies focus on the specific part of the characters and do not feed into real-time processing. A common way to create lots of characters is to use a character customization system, where the character's parts can be controlled by a set of customizing parameters, such as the eye size, the mouth position, and the hair color. One of the simplest ways to create a rich variety of 3D characters is to generate all the customizing parameters randomly. However, the results are affected by the number of the customizing parameters and their value ranges. For example, Final Fantasy XIV provides a few customizing parameters in narrow ranges. Good look characters can be created, but they are likely to be similar. While the game Neo 2 and the mobile application Custom Cast provides many customizing parameters in wide ranges, and unique but unstable characters may be created by random generation. The figure shows two results by generating randomly in Custom Cast, which seem to be hard to put them into the game scenes. So one promising idea is to control with machine learning. However, it is unrealistic to train the 3D models directly, because a single model could consist of thousands of polygons. And it is also difficult to prepare so many 3D character models as training data. Therefore, in our study, we decided to train the customizing parameters to avoid the characters with odd shapes. So next, I'm going to give an overview of our proposed system. The proposed system is divided into three parts: character customization system, data collection, and training neural network. I will talk about each part in order. First, we developed our own character customization system. The user interface is shown in the figure, where by dragging the sliders, we can adjust each part of the character, like the hair color or the hair length. Just like other games with character customization function, we use the skeleton to control the character. The skeleton controls not only the animation of the character, but also the deformation of the character. For example, the bones in the head are to control the deformation of the parts in the face. There are totally 96 bones in the base character model, and those bones correspond to 15 customizing parameters, which are shown in the red figure. The customizing parameters include 44 continuous parameters, such as head and hair length, and 6 nominal parameters, such as hairstyle and skin color. Most of the continuous parameters take values from 0 to 99, while the others control the eye color or hair color, whose value range is from 0 to 255. The second part is dataset collection. From the previous part, we can get many sets of customizing parameters by generating completely at random. So then, we have to classify the vectors into several levels. In our study, we classified them into 3 levels: good-looking characters as level 1, normal-looking characters as level 2, and bad-looking characters as level 3. The criteria must be clear, so we made some rules for the classification. A. Ignore hair color, skin, and clothes. B. If all the parts are satisfactory, classify as level 1. C. If serious problems with each part, classify as level 3. D. Classify the other as level 2. Let me take a few examples. Character A on the left has a good balance, as every part of the body and face is satisfactory, so we classified it as level 1. Character C on the right has a strange shape of head, and it has no eyebrows, so we classified it as level 3. The head of character B in the middle is relatively big, but it's not a serious problem, so we classified it as level 2. Note that it is difficult to find the relationships among the customizing parameters. That's why we relied on subjective aesthetics to classify the characters and try to use machine learning to find the features from the customizing parameters. The third part is neural network. We followed the rules in the previous part, so we removed some parameters like hair color and clothes style to reduce the number of input features from 50 to 42. The structure of the neural network is simple, which consists of 3 layers, and the hidden layer has 150 nodes. In an early stage of this research, we have tried to use deeper networks to increase the accuracy, but they didn't show notable improvement, so we finally decided to use this network. Finally, let's summarize the processing pipeline of the proposed system. Sets of customizing parameters are created by the character customization function, and they are trained as input features by the neural network. Also, our scene is built on Unity, so after the trained neural network is implemented into Unity without backpropagation to generate the required NPCs. Next, I will talk about some results of the training. From the confusion matrix, we can obtain the precision, recall, and F1 score of each level after training. From the table, we can see that generating only level 1 or level 3 perform better than generating only level 2. Because level 1 and level 3 have more specific features than level 2 does. There are still vague boundaries between consecutive levels. When classifying the characters, we found it hard to judge level 2 between the others manually, which leads to the low accuracy in level 2. Fortunately, the main purpose of the training is to avoid generating bad-looking NPCs. So if we employ only level 1 characters, it is still expected to get a good result. Then, we will move on to the evaluation of the study. First, we performed an evaluation on variety. It is quite hard to quantitatively evaluate the variety of NPCs. We did it in our own novel way to calculate the variety using a metric called loss of variety. In the calculation, we follow some rules that if any of the nominal parameter values are different, then the two characters are seen different. If all the nominal parameters are the same, and the distance between the continuous parameter vectors is greater than the threshold, then the two characters are still seen different. Otherwise, the characters are counted as similar. The formula and computation are detailed in the paper, so I'd like to show the result only here. G1 is the generation with the proposed method, and G2 is the generation with some simple limitations. From figure B, we can see that for every threshold value, G1 has much better variety than G2 does. We built a school scene on Unity to generate an NPC with a given request level. The proposed method generates a set of parameters completely at random and judges the level of the generated parameters by the neural network in a loop. The loop will break when the parameters are judged to have reached the request level. As shown in the table, the set of parameters of a single NPC was generated in 12 milliseconds, while the entire generation of a single NPC took 49 milliseconds. The generation of an entire NPC took a longer time because the process of combining the skeleton of the character and clothes took most of the time, and I think this process could be further optimized. We also built 3 classroom scenes for subjective evaluation. Let me play a short video to know more about the 3 scenes. In Scene A, NPCs are created completely at random. In Scene B, the generation is controlled by the proposed method with some manual limitations. In Scene C, the generation is controlled by simpler limitations that only the hairstyle, hair color, or clothes can be changed. Then, we conducted a simple evaluation experiment with 11 participants, in which each participant was asked to choose the most natural scene. From the pie chart, we can see that no one chose scene A, 4 participants chose scene B, and 7 participants chose scene C. As the reason for the choices, participants who chose scene C said that no character stood out from the collective. Participants who chose scene B said that everyone in the scene was distinguished, and there was a variety in the appearances of the NPCs. The number of participants was not sufficient, but we could still have some findings that the proposed method made the scene more natural to someone who prefers diversity. Finally, I will conclude the presentation with some remarks on future work. In conclusion, the system was able to create natural scenes with a rich variety of NPCs generated automatically, and combining parameter-based character customization with machine learning is effective. We left several issues out for future work, such as close coordination, NPCs with more gender and age, the improvement of the neural network, and to generalize the system by transforming the data collection into a semi-automatic or automatic step to apply to practical game development. At present, as seen in the video, we are focusing on increasing the close for close coordination using another way of machine learning to build more general diversity scenes. We thank all the volunteers who participated in the experiment and our sponsor. And thanks for listening.